A very good morning and welcome back to the second week of this introductory lecture on micro nanoscale energy transport. We will try to quickly conclude the generic introduction that we have been making so far. So, I would like to conclude by once again emphasizing where the macroscopic laws, we have seen the different regimes interpreted in different ways using mean free path, the characteristic length, Knudsen number. So, now I want to again recap, because this is very important when you are looking at transport processes, where you can use the macroscopic or continuum laws. So, you can say that generally the macroscopic laws break down under two conditions. Okay. So, one is you compare your characteristic length scale with the mean free path of the energy carriers. So, that is the first criteria to decide whether you can use the continuum equations or not. So, typically if you are looking at the illustration here, the figure A shows your classical continuum approximation, where the mean free path is much smaller than your characteristic length scale between say two plates. Okay. And here you find that these energy carriers are so many in number, they are densely packed and they have sufficient collisions with each other and also collisions with the boundary of the system. So, in this case you have sufficient statistical ensemble of particles to define macroscale properties such as internal energy, temperature, density and so on, right. Whereas, if you look at case B, so this is where your mean free path is much larger than your separation between the plates, and therefore, the chances of the inter carrier collision will be much lesser compared to the collision between the energy carrier and the boundaries of the system. So, in this case you will find new phenomena happening because of the more predominant collision of the energy carriers with the boundaries compared to the system A, right. So, this is what we attribute as subcontinuum phenomena. Okay. The kind of phenomena that you observe when you are much below the regular continuum approximation length scales. The other is your time scale. So, the time scale in this case also you have to be careful that it should if you take your physical system, okay, and then you have a time scale of this physical system, and then you have the time scale of the collision of these energy carriers. This is called the relaxation time scale. So, it is called relaxation time scale because this is the average time required for the energy carriers to collide and come back to an equilibrium state, to relax basically to an equilibrium state. So, this is called a relaxation time scale. So, you have basically a physical time scale, okay, number one. For example, this could be like a laser pulse which you are irradiating on a particular material. So, that is your physical time scale. So, this pulse width could be say nanoseconds, picoseconds and femtoseconds. The other is your time for the energy carriers to collide and come to a equilibrium state, and that is your relaxation time scale. That is typically, if you take the example of say electrons in a metal, it could be of the order of picoseconds, 10 power minus 12 seconds. Okay. So, therefore, if you are now irradiating with a femtosecond laser, 10 power minus 15 seconds pulse width. So, this is much smaller than your relaxation time, and therefore, again there is a chance that you are basically leading to a local non-equilibrium, and therefore, your continuum laws cannot be used. So, not only the length scales are important, but also the time scales are also equally important. So, there are cases where you have perfectly large dimensions, but you are talking about using very small time scales, and this can also lead to subcontinuum phenomena. Okay. So, therefore, you should also understand that anything dealing with subcontinuum, whether it is in the time scale or length scale, they are very difficult to observe with our senses the way we do it with your conventional measurement, and even the sensors that we are using, you cannot use them in the conventional way. For example, temperature can be defined only in the continuum sense. So, we cannot put a thermocouple when you are talking about a hot spot that I was explaining in the previous lecture in a silicon on insulator device. So, to measure the temperature of the hot spot at the level of nanometers, you cannot use a a thermocouple, because that the definition of temperature itself is not valid at such small scales, and therefore, I mean the thermocouple will not sense the right non-equilibrium phenomena that is happening. The temperature can be some kind of an average energy density, that is indicator of an average energy density, but it is not your equilibrium thermodynamic equilibrium definition of temperature. Okay. So, such kind of measurements will be very, very difficult therefore, to do at such nanoscales, and therefore, usually measurements are very hard and very difficult, and also very, very sophisticated, involving electron microscopy. You need to combine several things together. It is not just putting a thermocouple and just observing it. So, therefore, we are also relying on increasingly on the theoretical and numerical models, okay, by solving the subcontinuum transport equations based on Boltzmann equation and so on, doing molecular dynamics, Monte Carlo. These are the different subcontinuum levels of numerical transport that can be used, and they can actually give a lot of physical understanding before we can do these experiments. So, this is another very interesting picture that I got from a review paper some time back, and this review paper is from Professor Gangchen's group at MIT. So, this is very, very clear the way they have classified the different levels or regimes of transport on two scales. So, on the x axis what you have is basically the inverse of your Knudsen number, right. So, we define Knudsen number as the ratio of your mean free path to the length scale, and what is plotted here is just the inverse of this, and therefore, the one that is going towards the right end of the x axis will be the continuum, right. So, when the Knudsen number tends to go to very small values, so this particular quantity will be very large, and therefore, the portion that is towards the right end of the horizontal axis will be the continuum transport regime, and that is why it is called diffusion regime. Diffusion meaning that you have plenty of energy carriers which collide with each other, and therefore, the majority of the transport is by the diffusion or collision of the energy carriers. And on the vertical axis you have another non-dimensional ratio. This is basically the ratio of characteristic length to the wavelength. This is something also really interesting. If you are looking at subcontinuum, okay, how do you decide whether you are in a continuum or subcontinuum range? So, you look at the x axis, you define the Knudsen number, and accordingly you say for large Knudsen numbers you are looking at subcontinuum and so on. Now, within the subcontinuum regime, it is not just one whole subcontinuum regime there. Again, there is a regime where you have to be careful what is the length scale compared to the wavelength of the energy carriers. So, if you are talking about length scale of the order of angstrom, okay, now you find there is another regime coming out within the subcontinuum range where the wave effects become very important. Okay, and as I already told you that we have a wave particle duality, right. So, and you can always solve either of them, you can use either the wave approach or the particle approach, but the particle approach has a limitation that as long as your device dimension is much larger than your wavelength, then the particle approach can predict very well. But once the dimension falls below the wavelength, then what happens is the wave phenomena will become more important, and particle methods cannot predict the wave nature. So, therefore, you have to go into quantum mechanics, so which describes all these energy carriers in the form of waves, Okay. The wave nature has to be explicitly understood and therefore solved in order to describe basically the subcontinuum transport when your length scales fall below the wavelength of your energy carrier. Therefore, we have the two axes here, the primary axis, horizontal axis is your Knudsen number, the secondary axis is your the ratio of characteristic length to the wavelength. Okay. And when your characteristic length falls below the wavelength, so this is where your wave regime becomes important. You solve your Schrodinger's wave equation, which we will do in a few classes, introduce that and see how the wave nature can be explicitly understood and how it becomes important in subcontinuum scales. Whereas, if you are talking about the order of several hundreds of nanometers and comparable to the wavelength could be 1 nanometer, 2 nanometer, whereas the device dimension is of the order of 100 nanometers. So, in that case you are above the thermal wavelength regime and therefore, you describe by what is called as a classical subcontinuum regime or also particle based regime. Okay. So, these are very interesting regimes. So, you have to be aware that not only just using a simple subcontinuum model, but also depends on the ratio of the device dimension to thermal wavelength. You may also have to use sometimes the Schrodinger's equation. So, you cannot explain all the phenomena using the particle based method itself. That means, Boltzmann transport equation itself is not enough for describing all the phenomena. Okay. The most fundamental would be going to the Schrodinger's wave equation. Okay. Well, now again, so with this let us look at one example where we have a semiconductor device. So, this was one of the simulations I did a few years back by solving the Boltzmann transport equation. So, we have a system where you have a silicon film which is deposited, on top of this you have the silicon dioxide which is a dielectric. So, usually this is the substrate. So, the typical semiconductor device what I call as SOI, silicon on insulator. So, the SiO2 here is the insulating substrate over which you have silicon which has a very good thermal conductivity, whereas SiO2 has a very poor thermal conductivity here, and we just try to solve a simple heat diffusion problem in this system. Okay. The order of magnitude of silicon thickness will be the range of few tens of nanometers, okay, and the silicon oxide substrate might be maybe 5 times the size of the thickness of the silicon film here, and you have a homogeneous temperature defined at 3 boundaries, and at the bottom boundary you have a higher temperature. Okay. So, with this if you look at your solution of heat diffusion equation, where you apply your Fourier's approximation and then you solve it, you will be seeing a set of contours, temperature contours, and also at the same time you will not be seeing any kind of discontinuity in temperature between silicon and SiO2. Okay. There is no interface thermal resistance that we are modeling here. So, according to the macroscopic laws, your temperature has to be continuous at the interface and your heat flux also has to be. Okay. But now when you are solving this using a subcontinuum model, you see that now the major differences that you see in the silicon dioxide layer, where it is slightly tending towards the continuum level, you see your classical Fourier kind of equation pattern. You get these elliptical contours. So, the nature of the contours that you observe here typically are the ones that are predicted by solving the Fourier's equation, right. If you remember your solution of heat conduction equation. So, if you have a high temperature and then low temperature on the other 3 sides, this is how your temperature contours look. But you see within the silicon layer, where it is a subcontinuum phenomena, it is completely non-linear. So, you have a linear pattern of temperature outside the silicon layer, and within the silicon layer you have highly non-linear temperature contours, and there is also a temperature discontinuity which is happening at the interface. Okay. There is also slope discontinuity. So, you see that this high non-equilibrium process, if you use the Fourier's equation, obviously they will be completely failing to predict the values of temperature magnitude and also the qualitative variation of temperature within this particular silicon film. So, this is why we have to go to the models based on, for example, Boltzmann transport equation to understand this particular non-linearity at subcontinuum scales. Okay. So, therefore, just to finally conclude, so the way that we will be looking at this course on just the nanoscale energy transport, this concerns only the nanoscale part. The microscale part I will come back to that later on, but first when you focus on the nanoscale part, we start with the defining the energy states of carriers. Okay. So, that is the most fundamental level. So, where we apply the quantum mechanics, okay, and then we define these energy states of carriers, and from there we have to go to the macro scale level where we define properties, and therefore, we have to also understand how do we apply these quantum mechanics to certain systems. So, we will be applying it to systems which is semiconductor, crystals, nanostructures and so on, and we will see how these energy states get modified in this particular system. So, you have fundamental energy states which is for a single particle in a box or free electron or whatever, these are the theoretical ones, but when you apply it to a system where it is confined by certain dimensions and certain structure of the system. So, you have the energy levels or the fundamental energy states get modified. So, we will see how that gets modified. This is called dispersion of energy states. So, we will look at the dispersion, and then we will go to the macro scale by using statistical thermodynamics. We have to now collectively take an average of all the energy occupied by the carriers at different states. So, that will be done by using the statistical thermodynamics. Okay. And then, so this will be still an equilibrium value, equilibrium distribution, okay, from the statistical thermodynamics. For different energy carriers, they have different equilibrium distribution function. So, then how do we look at non-equilibrium, that is the transport of heat, for example. So, for that we will look at energy transport through non-equilibrium phenomena by solving the particle nature of energy carriers, say Boltzmann transport equation. And parallelly we will also look at some hand waving approach by using kinetic theory, and also we will show that using the particle based subcontinuum Boltzmann transport equation, we can take moments and then therefore we can derive basically the macro scale equations. So, essentially what I mean is that if you look at this particular picture, I still solve the Boltzmann transport equation here and here, okay, but you see that the Boltzmann transport equation tends to the continuum equation. So, therefore, it is automatically becoming a Fourier kind of a approximation in the macro scale limit. So, this is how you can show that you can derive all the macro scale equations from this fundamental equation, right. And we will also have a parallel treatment of energy carriers. That means, when I say energy carriers, this could be, for example, metals, it could be electrons. Electrons are the predominant energy carriers, so of heat or charge, electric current. And if you are looking at semiconductors, dielectrics, the predominant way of energy transport is by the vibration of the lattice structure. Okay. So, that we will assign a virtual particle called phonons. And then if you look at liquids and gases, it is molecules, but and as I said, the nanoscale phenomena is generally not observed in liquids, it is primarily in gases, the rarefied gases. Therefore, these molecules we will mostly focus only on the gas flows, and that is where the kinetic theory is also applied, right. So, with this I will like to stop the PowerPoint, and then what we will do now is start making some derivations. So, before we directly go into the nanoscale energy transport, we will start with the macro scale. So, because that is what is already known to you, we will derive the heat conduction or heat conduction convection equation first at the macro scale, then you understand what are the properties that is already known, should be known to you in order to solve this particular equation, and that is the starting point for your continuum solution, right. So, you assume that you already know certain properties, right, and how do these properties come from? They come from the micro scale. Okay. So, in order to make you a little bit more aware about this, we will first take the case of a closed system. Okay. So, I hope all of you are able to see the projection. Is that okay? Right. So, we take a closed system, some arbitrary system which is not a control volume because it is close to mass transport, and then you take a particular differential control element or a control volume, right, and let the surface area of this differential control volume be dAs, right, and the differential volume is dV. Okay. Now, the normal vector of this particular element is always pointed outward normally from the surface. So, this is your normal vector. Okay. And in order to look at only heat transport or heat transfer, okay, let us if you say energy transfer in general, you can have both heat and work transfer, right. So, you can say that there is a particular quantity of heat which is flowing into the system. So, this is positive when it is going into the system, and certain quantity of work which is done by the system. So, work done by the system is positive here. Okay. But when you are looking at only pure heat transfer, let us ignore the work interaction. So, we will simply ignore work transfer. So, that means there is always, of course, if you derive the energy equation very rigorously, the influence of work on heat is definitely there. It could be in the form of viscous dissipation, okay, or pressure work. Okay. All these are coming from the work which basically increase the internal energy of the system. But in this case, we now ignore those terms and derive only a pure heat equation without the effect of work. So, therefore, what will be the first law? First law of thermodynamics. So, all this is now macro scale. We can say this is your macroscopic or macro scale continuum heat transfer. Okay. So, can you write down the first law for this system and then so all of you should be able to write down the first law. Write down the unsteady first law, not the steady state form. Okay. First law, that means you have a time derivative also. So, you can for example ignore the macro scale kinetic and potential energies of the system. So, then what do you have? Change in internal energy, we will call du by dt. U is the total internal energy of the system. So, we are ignoring the macro scale kinetic and potential energies. So, this should be equal to q dot, right. So, this is for the entire control volume that we have represented. Okay. But the representation that we have q dot here, we can say this is dq dot for example for this differential element. Okay. So, therefore, we can integrate this for the entire control volume from the small differential amount of volume that to that we can integrate to the entire control volume, and we can also use the Fourier's law to describe the relation between Q and temperature. So, in a generic case, how do you write this? Without fixed coordinate system, in a coordinate free representation, del Q dot should be minus K into del T. So, gradient of temperature, right. So, obviously, you know why the minus sign comes here. Okay. So, this temperature gradient, if heat flows from higher temperature to lower temperature, will be negative. So, since our convention is heat should flow from high to low, so we put a minus sign to make this quantity a positive quantity, right. So, therefore, now for the entire system or control volume, all we have to do is integrate this over the surface area. Okay. So, this gives you the total heat transfer, and not only that, it is a little bit, you have to be careful with the normal that you are using. So, we dot it with the normal times dAs, right. So, therefore, as you can see that the direction of your heat flow and the normal are opposite to each other. Therefore, in order to make this heat transfer positive into the system, we have to put another minus sign out, okay, because the normal is pointing opposite direction to the heat transfer. So, you have to put a minus sign so that this quantity is positive, because now minus K delta T will be positive, but dotted with normal will be a negative. So, you put a negative sign outside, so that the heat flows into the system is positive, right. So, this is on the right hand side. Now, therefore, on the left hand side, we will introduce internal energy per unit volume. Okay. So, and then therefore, how do you write this in terms of specific internal energy? So, let us call this U as your specific internal energy. So, this is internal energy per unit mass. Therefore, for the entire volume, how do you write this capital U, or let us say d capital U by dt. Therefore, for the entire volume can be written as d by dt of integral u dv. So, here I am going to define slightly, again I will call this as internal energy per unit volume. Okay. So, therefore, this can be written as d by dt of, in terms of temperature, we can use the relation between du will be rho Cp or rho C into dt, which we can use here to write in temperature, terms of temperature. So, let me, so I will just use rho C and I will write this in terms of rho C and then dt by t, and this is over the. So, I am assuming rho C is anyway constant property. So, I can take it outside the integral, and this is now integrated over the entire control volume. So, now if I put them together, I have therefore rho C integral dt by dt into dv is equal to, I have integral k delta t dot ds. So, I will just write this as das here. So, I can now use the Gauss divergence theorem to convert this surface integral to a volume integral, and therefore, this will be divergence of, you have k delta t over the entire volume. using Gauss divergence theorem. Right? I am converting the surface integral to volume integral by introducing the divergence operator. Okay. So, therefore, now this can be written as integral rho c dt by dt dv is equal to, this is also a volume integral. Now, this is also a volume integral del dot k del t dv. Okay. So, therefore, if you take this integral volume integral common, you have rho c dt by dt minus del dot k del t dv is equal to 0, right. And therefore, in this case, in order to satisfy this particular condition, so your dv is not 0, right, you have a finite differential volume here. So, therefore, the integrand has to be 0. So, therefore, this will lead us from the integral formulation to the differential formulation. So, the differential representation therefore, now is rho c into dt by dt will be equal to del dot divergence of k delta t. So, this is your the generic heat transfer or heat conduction equation for a closed system. So, this is a coordinate free representation, and you can use whatever coordinate system that you are working with. You can use the corresponding gradient operator and divergence operator, and that should give you the the corresponding set of equations for that coordinate system. So, this is a generic coordinate free representation derived for an arbitrary control volume. So, now this is a conduction equation because we have not considered any mass transfer here. So, the same thing can be extended to an open system where you also have a mass flux. Okay. In that case, you also write the continuity equation to balance what is the incoming mass and what is the outgoing mass, and there is also what we call as enthalpy, which is advected by this mass. Okay. So, in the case of open system, if you want to do the same, apart from the, so we will just extend this to the case of an open system, because if you want to derive the convection equation, so you have to do this for the case of open system, and you also have to consider the mass transport and the corresponding transport of enthalpy due to mass. So, let us say the corresponding velocity, okay, entering of the fluid entering this particular control element boundary is u vector, and the corresponding enthalpy that is entering this particular control volume is hi, and you have a corresponding enthalpy of the fluid which is leaving this control volume, let us say that is u vector he. Okay. So, therefore, we can introduce net efflux of enthalpy, which is basically leaving this particular control differential control volume, okay, will be u vector times he minus hi. We will call this as u vector times h. Okay. I am just giving a, so this is h net, this is your net efflux of enthalpy, which is basically leaving this particular differential control volume. So, therefore, for the entire control volume, what is the net efflux of enthalpy? It is the integral of this over the entire control volume. So, control surface, because this is a flux is a surface related phenomena. So, therefore, we will just extend this to the entire differential control surface. So, for the entire control surface, So, the net efflux of enthalpy will be you have integral. So, you have UH and you integrate it over the differential surface area and over integrate it over the entire area. So, that will give you the net efflux of enthalpy over the entire surface. So, now the first law will now get modified. The first law for the open system, if you want to write it down, should now also include, apart from the terms. So, we had d by dt of integral u dv, right, and you also had the heat transfer by conduction. So, we had integral over the entire surface area k delta T differential surface area dAs, and apart from this now you also have the heat transport by the enthalpy, transfer of enthalpy. So, net efflux of enthalpy is also resulting in change in internal energy. So, that should come, because now the net efflux is actually leaving the system, that should come on the right hand side with a minus sign. Okay. So, you have this integral a u h into dAs. Is that okay? So, this particular term here is your net efflux, which is leaving the entire control surface. So, therefore, we have a negative sign. Okay. This is purely the heat transfer due to conduction. So, this is your conduction heat transfer and this is your advective heat transfer. So, now once again, if you apply the Gauss divergence theorem to the right hand side and convert the surface integrals to the volume integrals. So, and then write this in terms of rho c dt dv. So, everything is in terms of volume integrals. So, what do you have on the first term on the right hand side will become a volume integral and then becomes a divergence of k delta T dv, minus you have again a volume integral of divergence of u h dv, right. Is that okay? So, now I can again club these together, equate this to 0 and therefore, the integrand has to be 0. So, this will give me the equation to be the differential equation to be rho c dt by dt is equal to del dot k delta T minus del dot u h, right. This is my conservation of energy in the presence of flow, that is for an open system. Now, I can also introduce the relationship between H and the enthalpy and also temperature. So, for a incompressible substance, so now we make an approximation that the substance is incompressible. So, it could be, for example, a liquid, okay, or you can use a compressible substance like gas, but under the incompressible flow approximation, that is your Mach numbers are extremely small. In that case, the substance can behave as an although it is a compressible fluid, it is practically the regime that you are observing makes it an incompressible fluid. So, in that case you can say that your specific heat capacity due to constant at constant pressure and constant volume will be same, and therefore, your dH, which can be written as Cp dt, can also be written as just C dt. Okay. So, you use your relation this as C into dt. So, therefore, you can rewrite the above equation purely in terms of temperature. You get a equation for temperature which will be of the form. So, we will take this just a moment, we will take the enthalpy towards the left hand side. So, make this as an advection term, therefore, plus you have del dot u into rho c t here. Okay. On this side you have del dot k delta t. Okay. If your properties are constant, that is your rho c is constant, you can divide throughout by rho c and you get your energy equation. So, del dot u T is equal to, so you can write this as alpha, which is your thermal diffusivity, which is k by rho c into del square T. So, this is your heat conduction, or this is your heat transfer equation. Okay. This is your advective term and the right hand side is your diffusion term. Okay. So, once again this is in a coordinate free representation. So, you can use it in any coordinate system that you want. So, the reason that we have derived these equations which you are already familiar is to make you understand that we have made certain assumptions here. For example, we made the assumption that your enthalpy is related to temperature through the heat capacity, and also we have heat capacities coming here in the internal energy formulation, right. And therefore, you should understand that how do we basically fundamentally compute these property called heat capacity. How do we know this value? Where does it come from? Okay. Now, in our equilibrium thermodynamics, we assume that this is measured and known for most of the macroscopic substances, but then these are actually having a micro scale basis. So, you derive the equations to estimate the heat capacities from statistical thermodynamics, and that is what we will do slowly. Okay. But you should understand that even in the continuum equations, the parameters or properties that you use have a micro scale basis and they come from, therefore, understanding the micro scale heat transfer, right. So, this is why we are starting with what we already know. Okay. Although you should understand that fundamentally we should start with micro scale heat transfer, know things like heat capacity before we derive the continuum equations. Now, the next step that we will be doing is to quickly write down some of the continuum classical constitutive relations. So, we call this as classical constitutive relations. Okay. So, why do we call this as constitutive laws? Because in the above equations that we have written when we derived the conservation of heat. So, we for example, originally had the equation in terms of the heat transfer rate or the heat flux. Okay. So, now we wanted to close the relationship between heat transfer and the temperature through this particular relationship here, okay, and therefore, we could express your q dot like this, right. So, in fact, this should be a del q double prime, this is your heat flux and this is your heat transfer rate, we multiply it by the differential amount of surface area. So, this relationship to close is required, otherwise we will not be able to solve the energy equation. So, we need to express q in terms of temperature. Now, therefore, the resulting equation becomes a scalar transport equation in terms of temperature. Okay. So, this is called a constitutive relationship, and although this has been known without it has been originally proposed by Fourier without any rigorous background, we can also show from the microscale laws these classical constitutive laws can be derived. Okay. So, these are not something which has been simply proposed without very strong fundamental understanding. Although these were intuitively proposed, Fourier understood that your heat flux has to be related to your temperature gradient definitely, and he introduced this constant called the thermal conductivity. Okay, but this entire relationship can also be shown from the kinetic theory or also from the Boltzmann transport equation. We will do that in several classes down the line, but these are called as constitutive laws, and they are specifically used only in the continuum regime. So, we will see that number 1 is your, if you look at conduction, the most commonly referred one is the Fourier's law. You have also, you should remember, modifications to the Fourier's law. We have what we call as hyperbolic variants, okay, but the most commonly used one, which makes the, what is the nature of the heat transfer equation in conduction, the unsteady conduction heat transfer, it is parabolic kind of an equation. Okay. So, now there are variations to the Fourier equation which makes this heat conduction equation hyperbolic. Okay. They call this as telegraph equation. Okay. So, hyperbolic is typically a wave equation. So, that is why they call this as a telegraph equation, but let us not bother about that right now. So, we have already used the relationship between your heat flux and temperature gradient, which is stated in this particular way, and this is your heat flux in watt per meter square, and what is the unit of thermal conductivity here? Watt per meter Kelvin. Okay. Now, this is in conduction. What about in convection? Do you know of any other constitutive law that can be used in convection to relate the convective heat transfer to temperature? So, you have Newton's law of cooling, okay, which again states that your Q convective is equal to H A, this, if this is in terms of heat flux, we just say H into T surface minus T infinity. So, you can imagine case of a flat plate, flow over a flat plate, okay, and you have a velocity boundary layer and you also have a temperature boundary layer like this. Your wall temperature, this is your free stream temperature. So, you can either use Ts or T wall, whichever. And in terms of when you go to radiation, so what is the unit of H? Watt per meter square Kelvin. So, and finally, when you go to radiation, what is that you want to use to Stefan Boltzmann's law. Okay. So, that means your Q radiative is equal to, how do we write it there? Sigma into, okay, if you take a black body, let us first define it for a black body, it is just the surface temperature of the black body raised to the power 4. If you are talking about transport of heat between a black body and the ambient, okay, then we can say sigma Ts power 4 minus T infinity to the power 4. This is the net radiative heat transport between a black surface and the corresponding surrounding ambient. If this is not a black surface, but a grey surface, you introduce your emissivity, right. And for the black body, you have basically a distribution of the energy spectrum, okay, as a function of wavelength. So, in radiation you have spectral quantity, that means the energy or intensity is a function of wavelength, and it is also a directional quantity. Okay, it is different directions of the sphere or a hemisphere, the variation in radiation intensity is different. So, it is a directional spectral quantity. So, usually we average it over the directional space, hemispherical space. So, we call this as total quantity, but still total spectral quantity. So, if you look at the black body distribution function as a function of wavelength, we have the Planck's distribution function. You know, when radiation is taught, we just state this distribution function, but you should understand this is actually originally derived from the micro scale using statistical thermodynamics. No? So, this is related to your wavelength and also what else? The temperature of the particular surface. So, you can plot this for different temperatures as a function of wavelength, that is your Planck's distribution for black body, right. And in fact, if you go to nanoscales, now in the very recent years, you can see that the intensity of the spectrum, the intensity of the radiation emitted by these surfaces which are at proximity of nanometers can exceed the black body energy density. Okay. So, as I said, these are the new phenomena that emerge at small scales. Okay. So, classical theory states that none of the bodies can exceed the black body distribution intensity, but at nanoscales it is found to exceed. There are several phenomena attributed to that. Okay. They attribute this to photon tunneling, for example, and even at smaller scale they attribute it to phonon tunneling and all that. So, the gaps become too small that tunneling effects start appearing, like in quantum mechanics. Okay. So, you should not think that these are all the time, you know, valid. So, they fail at very, very small scales. So, these are valid only for the normal macro scale distribution. So, we will stop here, and then tomorrow we will also look at some other constitutive relations in fluid mechanics, mass transfer, in electrical engineering, and then we will slowly get into some physics behind the nanoscale transport. Okay. So, thank you very much.